Okay, good morning. We're going to go through another Unit 3 exam, as the Unit 3 paper is tomorrow for Edexcel Physics International A-Level. So the practical skills exam is worth 20% of the AS grade, and when you get into year 13, if you continue with the International A-Level, there's another practical skills exam called Unit 6 at the end. So this will be a quick run through. But please, if you looked at the one, I saw quite a few people had looked at the previous Unit 3 paper I've put in, which was January 24. I think we had about 100 and something extra views yesterday. So obviously these are good last minute revisions. Please, if you found it useful, please like, share and subscribe. So share it with your friends so we get more following. We will continue with these videos next term. So if you're going into year 13, we'll be doing papers on Unit 4, 5 and 6. I'm also going to be doing the non-international version of the Edexcel paper next year. So please make sure we get enough followers so it makes it worthwhile. Okay, so the first question is showing you a metal cube in this paper. So this is from October 2023. So the cube, they've given you the record of the measurements made of the length, width and height. So, and they've done 3 measurements, okay, in different places on the cube, which is always a common question they ask you in measurements techniques. So this exam is about techniques, practical things. There isn't a syllabus list for it. You just got to get used to it. There are some YouTube videos where people do the core practicals and they explain what to look out for, so you should have a look at those. If I find any, I'll actually share them in the videos as well, so you can actually share other people's videos. So have a look in the videos that I've put on the channel, and you may find other people's videos which will help you look through the skills. Okay, so there's 3 different measurements made of the length, the width and the height, and they're giving you the mean measurements of each. So the key point here is they've made, or the student has repeated measurements in different places on the cube. Well, obviously a cube is a regular shape, so the length, width and height should all be approximately the same value. So you should identify a measuring instrument for these measurements. So it's about 20 millimeters, so about 2 centimeters across each way. So normally we wouldn't use the micrometer, and I noticed some students in the mark scheme, they accept the micrometer. Okay, so obviously the micrometer is for smaller measurements, usually for diameters of wires. So what you would use is normally calipers, and you can now get digital calipers and vernier calipers. Now vernier calipers can measure as up to 0.1 millimeter. Okay, so you'll notice the measurements are to 0.1 millimeter. Micrometers measure to 0.101 millimeter. So really, micrometer is not the standard technique for measuring the instrument for measuring 2 centimeter gaps. And then now they got digital calipers, which we got now in our school, and they also can measure to 0.01 millimeters. So probably if we were choosing, if we had a choice, we'd probably use a digital calipers if you had all 3. Okay, so that's just a note. You need to know the resolution of each. These are the resolutions of each. These are the kind of things you need to know for this exam. The student then noticed that the uncertainty in the mean width, so these values, is larger than the uncertainties in the mean length and the mean height. So how did they recognize that? Suggest why. So it doesn't want you to say how they recognize it. They want you to suggest why the uncertainty in the mean width is larger. Okay, so the mark scheme for accepted answers, more than one accepted answer. So I show you the mark scheme where you can have a variety of answers there. Okay, so this is question 1, question 1b. So 1b states that the 20.0 millimeter measurement is an outlier. So one of the measurements, that third one just above this one, is an outlier or an anomaly. Yeah, so you could say that one of them's an anomaly. Okay, but why would that be? Suggest why. So I would go a bit deeper. Either the cube is not quite a cube, that different places along the width are different lengths. Yeah, So you could say the student misread the scale, that they made a mistake if it wasn't a misshapen cube, or the cube is not uniform. In other words, if it's not uniform, it's not actually a cube. Maybe the cube has been damaged. So these are all reasons that they would accept. So there is no one answer that you can put. Now you can have a look at the other answers and stop the video for 1B and 1C as well. Okay, 1A is there as well. So you can put any of the answers from the mark scheme for the 1 mark. Question part C, they want you to then determine, let's get my papers just in the right place to start at the top, determine the percentage uncertainty in the mean length. So you just have to average them. Okay, in the mean length the average is 20.2, and so you need the mean length to be able to work out the percentage uncertainty. And in your exam, the percentage uncertainty is half the range divided by the mean value. Okay, and half the range, it was varying from 20.3, yeah, so we're talking about the mean length. So it was from 20.3 to 20.1, so the mean is 20.2, the range is 0.2 millimeters, so the range is 0.2 millimeters, but the percentage uncertainty, you always will use the half of the range, because that's how much the mean varies each side, minimum and maximum, and that gives you a value of 0.5%. Okay, so remember, this equation will come up in your exam. The student in part D says the student measured the mass of the metal cube as 72.8 grams, and if you have to use kilograms, make sure you change the number to 72.8 times 10 to the minus 3 if in kilograms, using a top pan balance. They want you to show that the density of the metal is about 8,800 kilograms per meter cubed. So they want you to use kilograms per meter cubed. Sometimes they ask you to use grams per centimeter cubed. Okay, so obviously the volume is the length times the width times the height. You put the values in, and it's easier just to use standard form, put the times 10 to the minus 3 there. I had a student who did it in millimeters and then tried to convert it and got it out by a factor of 1,000. So that's easy to lose those marks. So just let your calculator do the work for you and write it as standard form. Okay, that gives you a volume of about 8 millionth of a meter cubed. Okay, because remember, it's 1,000 millimeters this way, 1,000 millimeters that way, and 1,000 millimeters depth. Okay, so each one brings in a factor of 1,000 when you're converting from millimeters to meters. Okay, and then you divide the mass by the volume. Make sure you've changed the value to kilograms, and the answer to 3 significant figures is 8,830, which is approximately 8,800 to 2 significant figures. I always like to do that to show that I know the importance of when to quote which significant figure, because here they want you to tell them it's about 8,800. That means two significant figures. Okay, that's question 1 done. And question 1 has another part. I apologize. It then goes over the page, and the student is told that the cube is made from copper, bronze, or brass. So we don't know which. So you've got to work out which one it is. The table shows the densities of these metals, but the student estimates her percentage uncertainty. Yeah, because it's a she. Her percentage uncertainty is in the percentage value of the density block. So it's her value of the density. Her value she estimates to be 2% out. So if it's 2% out, it could be 8,830. I'm using 3 significant figures, more accurate than the 2 significant figures that we used at the end. So it's plus or minus 2%. Well, 2% of 8,830 is about 180. Now you can round these values up. You don't have to give the accurate value. So we know that the range will be maximum of about 9,010 and a minimum of about 8,650 when you add or subtract the 180. And only copper from the table lies in this range. Yeah, copper is between that range. Bronze is just outside that range, and brass is even a bit lower. So you have to make sure you do that. So this is a common thing, to compare your value with a known value, or known values in this case, and to decide how far apart they are. and whether it's feasible to assume it's copper. Okay? So these are the skills: percentage uncertainties, resolution. These are the key words you need to know for this exam. Question 2, a student, this is more application of electricity. Student models a safety system used on a railway. The two parallel 30 centimeter rods, these ones, model the rails. So these are like the rails on the railway. And then the rods, these rods are fixed 5 centimeters apart and are connected to an ohm meter. Okay, so an ohm meter works out the resistance for you, and a movable copper rod models the train. So this is representing the train as it moves across the rails. The rod completes the circuit from here. Remember, the ohm meter has its own power supply in it. So basically, the current is going through there back to the ohm meter. And obviously, as the train moves further apart, the resistance increases because the length of the copper that's used increases too, and length is proportional to resistance is proportional to length. Okay, so that's the basic workings of the theory. As the distance x from there to there increases, the resistance of the circuit varies. Well, obviously, as x goes up, r will go up in direct proportion. Okay, because x is the length, represents the length, and it's going to be 2x plus whatever this 5 centimeters is. Okay, so the total length, and you'll see this in the next, is 2 lots of x, because it's going to go there and back again to the ohm meter, plus the 5 centimeters. Yeah, plus 5 centimeters. So depending on what you're going to do, because remember, the equation for resistance is R equals rho L over cross-sectional area, and that's what they're going to use. This is the theory of this question. Describe how the student could determine accurate values. So that's your job, is to describe how you could determine accurate values of x and r. Okay, so I'm going to do this one last because these are ways of checking for errors and uncertainties or minimizing them. Ensure the movable rod is at right angles. Yes, we want this one to be at right angles to the 30 centimeter rods using a set square. So they always ask you questions about how do you make sure it's perpendicular. You use a set square. So you can even draw it on there. If the set square is tight fit 90 degrees here, then you know that's at right angles. Then this equation will be known accurately. If it's not at right angles, you'll have to do, so you'll be inaccurate. Okay, so that's accuracy. So using a set square comes up in most exams. Measure x with a ruler. Yeah, so if you're measuring x, you obviously need to measure x with a ruler. Yeah, I'll do it on each side. Yeah, and calculate the mean or the average. Yeah, you should normally use mean. So you take the x here, you take the x there, and you make sure you've checked that they're the same value, so you can get a mean value for x, because remember, we would need accurate values of x. Okay, they always say what you're measuring it with. Don't just assume the examiner knows that you know. Okay, treat the examiner as if he doesn't know. Okay, ensure the movable rod is making good electrical, so this is for resistance. So this, the first two were to make sure that you got accurate values for x. Here is a good one. Ensure the movable rod is making good electrical contact with the two fixed rods by ensuring the rods are clean. For example, if there's any oil or something on the material, it will reduce the conductivity. So you could actually sand it. Yeah, that they haven't put that in, but they want you to mention that they should be clean to make a good contact. Okay. And the fourth mark could be either check for any zero error on the ohm meter, which is why I wanted to put this one down here as well. So the ohm meter is on the correct range. Set the ohm meter on the correct range as well. That's the other thing. So you get an accurate value, a precise value, because you can set the ohm meter on milliohms or whatever. Make sure it's set on the one which is the most accurate for your readings. And then you could repeat an average resistor readings. Yeah, so the average again should be a mean. Okay. All right, so I hope that helps with this question. Then they've given you a graph of resistance against X. So as X increases, yeah, the resistance increases, but you notice it's not going through the origin, because remember, X is not the total length. Okay, so they're going to ask you about that. So the student measured these values, and the other thing you've got to notice is they're using milliohms. So again, setting the ohm meter on the most appropriate scale to get your results as accurate as possible. State why the line of best fit does not pass through the origin. Well, this is linear, but you've got to ask yourself, is resistance directly proportional to X, or is it directly proportional to the total length? Yeah, so that's for you to think about. Yeah, is R directly proportional to X? The answer is no, it's not directly proportional. It's proportional to X, but it's not directly proportional to X. So, but they would accept, if you look at the mark scheme, we'll have a look at it in a minute, some kind of systematic error is what they're trying to get at, because it's not going through the origin. However, they would accept this, that there's some kind of systematic error or zero error on the ohm meter. But that's not actually the correct answer. It's because when this is actually the correct answer. So this OR mark that they get. So this is what you should really explain. When X is 0, R does not equal 0, because L does not equal 0. Remember, we said L is going to be equal to 2x plus 5 centimeters, which is the movable rod in between them. So the total length is not only X. So it should, that's the 5 centimeters, if you like. Yeah. Well, they put X, so they should have here, if they put 2x plus 0.05 centimeters, if they're doing it in meters, that's what it would be. That should then go to the origin if they put this on the x-axis. So when x equals 0, r does not equal 0, as the ohm meter, yeah, because they want you to say y, the ohm meter measures the resistance of the movable rod, yeah, plus there may be other things, that there's the connecting leads themselves could be having a little bit. Remember, copper doesn't have a very high resistance. Anyway, okay, so I hope that makes sense to you. Okay, so it's not really a systematic error, it's just the wrong graph they're plotting. So now, the total length of the copper in the circuit is given by what I mentioned, 2x plus 0.050 meters, if you're doing it in meters, which is what they put on the graph. Okay, the copper rods have a diameter given in millimeters. So remember to change the diameter to meters. And then you want to work out, remember the equation is R equals rho L over A. We want to work out the cross-sectional area. So it's pi r squared. So you change the D to the R. So this is to work out the cross-sectional area. You get 1 mark for that. Okay. And then you put, so we know A. Now R over L from graph, you could possibly get it from the gradient, but of course remember it's X. So R over L, value from graph, you can get them, yeah? So what one of my students did, which is what I thought was clever, is look at the graph. At 1 milliohm, what was the length? Yes? So if you do it for 1 milliohm, then you know the top of the equation here is going to be, I've changed the subject of the formula here. If you change it, you want to work out the resistivity, remember? We want to work out the resistivity. So if you change the subject of the formula around, resistivity is going to be the resistance times the area, which we've worked out, divided by the length. And R over L can be obtained from the graph if you take values from the graph. So I think the quickest way is to look at it, example, at 1 milliohms, because it gives you a nice value. X then is 0.185 on the graph. And remember that length is 2 times the X, yeah? So 2 lots of that, plus the 0.05 for the movable rod, and you'll get a length of 0.420, which corresponds to the 1 milliamp. Then you put the values in. 1 milliamp, I put them upside down initially, these two values. I was not thinking clearly, so anyone can make a mistake. So I have to X it out, put it in correctly. So this is the value I used from the graph. L is then the calculated value used to get the X from the graph, put it in, and this is the area. Put the answers in, you will get about 1.70 times 10 to the minus 8 ohm meters, which I've shown the examiner. There's my answer. Okay, hope that makes sense. I didn't show you the mark scheme for the previous part, which is what I wanted to do. So we're on question 2, I believe. So for question 2, here's the mark scheme for this question, yeah, up to part C, some of it. There's 2A at the top, and I'm just going to move it up so you can pause the video up to part C, yeah, and part D as well while we're at it is at the bottom. So remember, you can stop the video and have a look at the mark scheme to see if what you've put down merits a mark or not. Okay, so that's question 2. The last part of question 2 we haven't done. The safety system on the railway estimates the position of the train, yeah, or any train on the track using a resistance measurement. So they're using resistance. Now we already know how resistance varies with the other variables. Now over time, it says the rails become worn with continual use, so their cross-sectional area decreases. So in this equation, A goes down. Well, if A goes down, then R is inversely proportional to A, so the resistance will increase. So if it's worn, it will misrepresent the resistance. So this is what they want to explain, how the decrease in the cross-sectional area through wear and tear affects the estimate of the position of the train on the track. Okay, so it thinks that the area is bigger than it is, but in fact it's lower. As the cross-sectional area of the track decreases, the resistance increases. It's just as I've just explained. So the safety system will estimate the position to be further away than it actually is. Okay, hope you can work out why that happens. Yeah, so you have to use your ability to solve the mathematical variation of how the resistance is dependent on the area. So if this goes down, this goes up more than it thinks, and it doesn't know that the track is worn, so it will give you the wrong position. So that's the 2 marks. You get 1 for each line. Okay, you can have a look at the mark scheme later on if you want to go back to it. Question 3 is then about a wave traveling in water. So the wave is going this way, and a student's investigating how the speed varies for water. It varies with depth, is affected by the depth of the water. So the only thing in water that affects the speed of the wave is the depth. Okay, so that's why, for example, waves by the shore are being caught up with the waves behind them, because obviously as they come and break at where the sand is, for example, they're slowing down due to friction. She filled a 40 centimeter long plastic tray, yeah, with water to a depth D. Yeah, they haven't told us if the plastic tray is transparent or not. Yes, whether we can see the water level from the side. But she raised and released one end, so she basically picked this up and caused one wave to go to the end and then bounce back. Creating a wave which travelled along the surface of water as shown. The wave travelled to the far end of the tray and was reflected, so basically it goes this way and bounces back. The student had a meter rule and a stopwatch, so these are the equipment apparatus that they used. Okay, often when you're planning an experiment, you also need to think about what equipment to use. Okay, so you have to be able to plan experiments, write down methods, etc. So describe how the student could determine accurate values for, again, so similar to the previous question, or one of the previous questions, for D and for V. So how would you measure D accurately, and how would you measure V accurately? Okay, so what do they accept on the mark scheme? So question 3, the mark scheme for part A is here. Yeah? Let's just look at 3A and 3B. Okay, so we've got 3A and 3B you can look at later. Here is 3A underneath the question. So they want you to ensure the meter rule is vertical. So you're going to use the meter rule to measure the depth here. So you put your meter rule at the end, yeah? Or do you put it inside? So imagine you put your meter rule here. You make sure it's vertical. How? Again, use this set square. Okay? So one way of doing that to make sure the meter rule is vertical, to make sure you're measuring the distance D accurately. And then so that's 1 mark they want you to get. Measure D in multiple places. Okay? So how will you measure D in multiple places? So you could put it in the water, but that's what I said. They didn't tell us if the water depth if the side of the plastic is see-through. So you'd have to then talk about that, okay, measure D in multiple places and calculate the mean. But as long as you say that, they'll give you the mark. Okay, the alternative methods are there for doing it. Measure the time taken. So this is now for the D, yeah? And then it says measure time taken for the wave to travel at least 2 lengths of the tray. In other words, it goes there and back, okay? Because it may slow down, who knows? But you've got to do it. So basically they want you to do it over the 2 lengths. Or repeat this and calculate the mean. So they want you to repeat it. So this gets you a mark by saying to go 2 lengths, or repeat the measurement taken for the wave to travel the length of the tray. Repeat this and calculate the mean time taken. Yeah, and therefore the average time gives you the average speed. And remember, they're using mean and not average. Okay. Or it says use a video camera to film the wave to determine the time taken. Well, you have to know how to do that. So one of my students put this answer down, which makes me suspicious that he'd already looked at the mark scheme, because it's not something that I've discussed with them, because a camera has a certain number of frames per second, so you can use a camera to work out how long it took for the wave to go across by freezing the motion of the video. And then it said calculate V using average time for the wave to travel 40 centimeters. In other words, you're doing distance over time. So these are all the different methods of getting the 4 marks for distance and then for time to work out the speed. Okay, hope that makes sense. I just thought it'd be easier to do it through the mark scheme. Okay, so that's the 4 marks basically is part of the method. If you're planning an experiment, you should always know how to get accurate values and how to make sure you haven't got any errors. Again, vertical, parallax errors, make sure you're measuring at eye level as well. Because although it could be looking like it's vertical this way, it could also be slanted backwards, so you have to make sure it's vertical in more than one plane. I hope that makes sense. Okay, so that's question 3A. 3B, it mentions the student was given a formula. The formula is given for the speed of water, v squared equals kd, where k is a constant. Describe how the student could use a graph to determine a value for k. Well, if you've put v squared on the y-axis and you put d on the x-axis, remember we're seeing how distance affects the velocity. So if you put v squared on the y-axis and d on the x-axis, the gradient will be whatever's in front of d, y equals mx plus c. This is a common exam question to show the form that you're given of the equation. So we know the intercept is 0, but they haven't asked us that. Describe how the student could use a graph to determine the value k. Well, the gradient of the graph, if you do v squared against d, will be k. Yeah? So you put v squared there, you put d there, and it should be directly proportional because the intercept is 0, and the gradient will be delta y over delta x. Yeah? So this is a common question in Unit 3 and Unit 6 papers. She then determined the speed v, yeah, for the 3 depths. She only did 3 depths. Is that a good method? She calculated the value, so she calculated the values of k for each depth. So, yeah, so that's what she did. Well, how does she do that? So you can just, so k would be v squared. Remember, k would be v squared over d. Okay, so you put that in your calculator and you work out that is going to be that. But they want to criticize the recording of these results. So again, I'm going to show you the mark scheme. You'll notice this one is to a decimal place. These ones have no decimal places. These are all to the same number of decimal places. And these ones are, again, to different number of decimal places. But let's see what else you can put to get the graph mark for getting these values. So it's 3b2. Okay, so we looked at 3a, 3b is shown there, and 3b2 and 3b3 are shown here. So the whole mark scheme. So there where they want inconsistent decimal places, inconsistent significant figures for k values. Yeah, now if you're working out k from another value, you should use the same number of significant figures as your raw data. No evidence of repeated measurements, not enough different depths, so not enough range of data, and k is equal to 9.9, incorrectly rounded to 9.96, it says. Okay, I haven't checked that. It's part B, part 3 is also given to you there, so you can stop the video, have a look at it once we've gone through 3b3. Okay, so over the page, what do they want you to do? Once you've got that, they want the students then suggest that the value of K should be equal to the gravitational field strength. Now, it doesn't matter whether it's correct or not, the theory, you just got to work it out. Discuss whether it is likely that K is the gravitational field strength based on the data given. That's what they mean. Your answer should include calculations where the average K from the data given is equal to 9.71. Yeah? So that's given to you. You just take the average K here and you'll see that it's 9.71. Okay? Once you do that, you can then say, well, the gravity is 9.81. Well, it's not that far away. The percentage difference is 0.10 divided by 9.81 times 100, which is only approximately 1% difference. So K could be mathematically equal to G, as the percentage difference is very small. 1% is easily covered by just uncertainties in measurements. Okay? That's what they want to do. So again, they're doing a percentage difference in your calculation. Okay, the next question is question 4. Photoelectric effect. The student investigates the photoelectric effect using the apparatus shown. So you have to look at what's in there. They've got a colored filter, they've got a photocell. So this is the sensitive part that will determine the light going in, and the voltmeter is measuring across the potentiometer, which is basically a long wire that you can adjust as a variable resistor in parallel with the power supply. So he used a source of white light and colored filters to shine different wavelengths, lambda, of light onto the photocell. Well, how do you know the colored filters are pure greens or pure blues with only a single wavelength? Because remember, they'll have a range of wavelengths that they can get through. So photoelectrons, it says, were emitted with a range of kinetic energies, creating a small current in the photocell. They haven't shown us where the current is measured in the circuit. They've only shown you a voltmeter. So then it says using the potentiometer. So the potentiometer is there. Yes, there's this resistor in the diagram across the photocell. So the potentiometer is across the photocell. So the photocell's there in the circuit. So the photocell presumably is then giving off some value of current, yeah, due to the electrons being emitted. It's affecting the flow of current. It says as the potential difference across the photocell increases, yeah, so this has its own voltage across it due to the photoelectrons being emitted. As the potential difference across the photocell increased, the PD goes up, the current in the photocell decreased. Okay, so the current in the photocell decreased as the voltage there increased. Okay, so that's just telling you PD goes up, the current goes down. So they probably want you to think about why. He measured the potential difference V here when the current in the photocell was 0. Where's the ammeter? They haven't shown us. He calculated, so when the current is 0, they've put, that's what that is a controlled variable, yeah? So when the current in the photocell is 0, it's when they take in the readings. He calculates the maximum kinetic energy, E max, of the photoelectrons. Remember, the potential difference that they put could be the cause of stopping the photoelectrons, because they could oppose the movement of the electrons which are emitted until you got 0 voltage, and that's one of the core practicals that you need to have covered in this syllabus, okay? Or at least you need to know the theory. So the data shown here shows you the maximum energy at when the current was 0. The voltage allows you to work that out theoretically, and they've given us the wavelength of the light for each of the filters, presumably, okay? So it goes from 620 down to 436. The table shows the student's data. And then they want you to plot a graph of this value, E max, yeah, which is when the current is 0, on the y-axis against 1 over lambda, yeah, not lambda, on the x-axis, on the grid opposite. Okay, so they're giving you graph paper. And then we're going to look at the mark scheme to see how you get it. Well, if lambda is in nanometers, what are you going to put 1 over lambda in? See, so you put 1 over this value, make sure you know it's in nanometers there. And then if there are 3 significant figures here, you should have 3 significant figures in your data, like I mentioned to you before in a previous question. So they want you to use this column for your process data. So they want you to work out that you have to have values of 1 over lambda. Okay, so we're going to look at the mark scheme. Okay, trying to see where the graph is gone. Okay, so the mark scheme for this question is here. So here is what they're looking for. 1 over lambda correctly rounded to 3 significant figures, 1 mark. So if you put the values in correctly to 3 significant figures. Now here they've done 1 over lambda in their table, and they've changed it from nanometers to the -1. Remember, it's 1 over lambda. So if you put nanometers, you get 0.000161. So they've done 10 to the 6, and they move the decimal place 3 places the other way to make it easier to plot. So you see this, if you do it this way or this way, which one's easier to plot? So that's just a student's choice to do that. Both axes must be labeled with the quantities in units. So here the energy maximum is given to you in the value of 10 to the minus 20 joules. They've just written it in typo. When they typed it on the side of the graph, they probably couldn't get it right. When you're doing it, you've got to make sure you put the units correctly. That says 10 to the minus 20 joules. That's where it comes from. And then on the x-axis, if I can just move the graph slightly further up so you can see the x-axis. So 1 over lambda is 1 times 10 to the 6. You see this is just a typo again. 1 times 10 to the 6 meters to the -1. So they've used, instead of nanometers, they have used the value here, which is 10 to the 6, and it's a good thing that they did that because it's easier to plot. You don't all those decimal places. Okay, so all you're doing is you're changing this the values from a very small value to 1.7 by changing the standard form. Okay, so once you've done that, what are they giving marks for? So going back to the mark scheme, axes labeled with quantities of units on both sides correct. Sensible scales, so they're going up in 1.0 values at 10 to the minus 20 joules. So each one is worth 1 times 10 to the minus 20 joules. So it's a round number. And here they're going up, and neither of the values are going down to 0 because all the data is in a higher range, so it gives them a better line of best fit. Okay, so you don't have to go to 0. I've taught my students, if you're not going to 0, show a zigzag line to show that you didn't go to 0. Okay. The other thing is, so they're going up in 1.0 times 10 to the 6. So again, I always tell my students sensible scales, when they talk about it, means multiples of 1, 2, 5, or 10. Yeah? So sensible scales means multiples of 1, 2, 5, or 10. You don't, obviously 10 is a multiple of 1. You don't use 3s, 4s, 6s, 7s, 8s, or 9s, because then it makes it difficult to do the plotting. Accuracy of plotting, they will check it in the exam. If they notice your values look far away from the line of best fit that you've drawn, they will look at the 2 which are most furthest away, and if they see that you've made a mistake, you'll lose your 2 plotting marks. And finally, you get a mark for drawing the line of best fit. So that's how you get your 6 marks for the graph and the table. Okay. After that, when you're doing it, they want you to work out the gradient. I've put my values, which I've used the same as the examiners. Yeah. The gradient can be shown from here to here. The reason I chose that is because here you got a round number, here you got a round number. So the value here is easy to delta x, and delta y is positive, so it goes from 6.6 up to 12.8, so the variation is given there and there. It's always important that you use a large triangle to work out the gradient, because you'll have a smaller percentage uncertainty in your final calculation. Okay, and if you can work out the units, you need to put it, because you could lose a mark if you don't put the correct units. So once you've done that, on your graph, you need to make sure you have done all of that clearly. So show your triangle, and then it says, part 2, 4a, part 2, it says a relationship for the maximum kinetic energy of the emitted electrons and the wavelength is given by this equation. So it's basically, this is the photoelectric effect, and instead of HF, they've given you HC over lambda because you're measuring the wavelength. Yeah, so you've got to be able to see that this is HF. Yeah, because remember, HF equals HC over lambda. Okay, because of the equation for velocity, wave equation. Okay, so once you've done that, they want you to use your knowledge to work out the Planck constant. Yeah, that is linked to the gradient of the graph divided by c. Okay, so let's see what I've done. So I've changed the subject to formula because we know that on the y-axis we put the maximum energy. So E is on the y-axis, so there's my y value. And on the x-axis we put 1 over lambda. So this is 1 over x. 1 over lambda is the x value. And the intercept on the graph, which we haven't looked at, would be the work function. So this value is the work function from the theory. We're not looking at the intercept because they want us to look at the gradient. So the gradient m will be equal hc. Yeah? So m, the gradient, must be equal to hc, as we've seen from this y equals mx plus c format. So remember, in these units, they're looking at your mathematical skills of knowing what a straight line graph is. In A-level physics, you have to be able to get any equation into a straight line graph to be able to work out an unknown or whatever. And here they want you to work out what h is based on the gradient. So using this format, you can see the gradient is hc. They want you to work out h. Therefore, h will be m over c, the gradient divided by c, where m is the gradient of the graph that we just calculated. Okay. Now then they want you to actually come out with a value. Well, we did the calculation of the graph on the gradient on the graph, and it comes to this value. So you have to look back at my graph to see how I got 1.24 times 10 to the minus 25 joule meters, divided by the speed of light, which is on your data sheet, and you'll get the value of h, which is a bit out because the true value is 6.6 times 10 to the minus 34. So they want you to calculate the percentage difference of your value and the accepted value, which is here, and you can find this on your data sheet, for the Planck constant. Remember the percentage difference. So again, they're doing a percentage difference between a true value and your value. The percentage difference is take away the two values from each other and divide by the true value. If you don't have the true value, you would use a mean value if it's not a known constant. Both of them are 10 to the minus 34, so you can actually calculate that out, and you'll see the percentage difference is 38. Okay? So you're beginning to see that these techniques are used, these skills are used in all the questions the same. Finally, part B, the last part of the question. For the student's investigation involves a small random error and a large systematic error. Okay? The student's investigation involves a small random error and a large systematic error. So this is really good practical to go through before your exam tomorrow, because you need to know what is a random error, what is a systematic error. Random error means it can go up or down. Systematic error means there's a problem in the system, like a zero error that you haven't taken into consideration, that will always go like too high. The readings will always be too high or too low. For example, in a rail question, a systematic error could be that you didn't have good contacts between the moving copper and the copper rods that it was landing on. It wasn't making a good contact, so it was increasing the resistance and you didn't know why. So that would be a systematic error. Okay, so random errors could be that you're not measuring at eye level. Parallax errors would be an example. One time you're measuring it too high, one time you're measuring it too low. So it says for each of these, suggest the source of the error, whether it's random or systematic, and a realistic modification to your procedure, which would reduce it. So what are they accepted in the answer? So the answer says, for the random error, for the random error they've put, it's difficult to judge exactly when the current becomes zero. But first they didn't show us how they measured the current being zero. It's because obviously you need to have a very accurate meter to be able to get exactly when it's zero, because if you're only measuring it in amps, it's not accurate enough. Maybe there's still current going through and your ammeter isn't sensitive enough. So the exact stopping potential will be difficult to identify. So that you haven't said why yet. So you've put what it could be, because remember the question's asking for each of these suggests a source of the error, and a realistic modification. So the modification would be use a more precise ammeter. And here they put picoammeter, and that measures times 10 to the minus 12 amps. Because remember, we're measuring tiny amounts. We want to get the maximum kinetic energy of the photoelectrons. So we're talking about tiny currents. We want the last electron to be stopped. So we want as accurate a meter as possible. Okay. So you don't need to put example picometer. You just need to use a more sensitive ammeter. Okay. Alternatively, for random error, you could put there is background light level, which could affect the wavelength or the color that you're putting in. Obviously, you're putting a single wavelength in using colored filters. Yeah. So you're using colored filters, but it says there could be background level. So you need to make sure you've blocked the background light level. Yeah. Because if you haven't done it the same each time, sometimes it could affect the results one way or another. Or it says put the colored filter, simple way, directly above the photocell, so no other light can affect the photocell. Okay, so that's a good thing for you to think about. And then for the systematic error, remember you need to have the answer. You suggest the source of the error and a way of modifying it to reduce it. Okay. For the systematic error, they want you to use color filters do not give monochromatic lights. So if they don't give monochromatic light, that wavelength that you calculated is not accurate. Yeah, so it could be that it could be too low an estimate each time, for example. Or the colored filters could give a range of wavelengths. This is all the same thing, or frequencies. Or colored filters might be damaged and let through other wavelengths, etc. So you get the point. This is all the same point. Yeah. So it's different wordings that students had used and they've accepted them on the mark scheme. Use a monochromatic light source would be a way of doing it. You don't have to say how, but it shows that you understand that the wavelength needs to be a single wavelength for the data on the graph to be accurate. Yeah? Or use a narrow wavelength band, or use a light source with a single color, example LEDs or lasers. So again, this is all the same solution to that systematic error. Another systematic error, which we mentioned before, is a zero error on the meters. Yeah. So if you say that, you get a mark. Check the ammeter reading is 0 while no light is shining. Yeah. So this is the solution to this problem. So this is ways of you thinking about any experiment you do. You need to know systematic errors, causes, and solutions, and you need to know random errors, causes, and solution. Okay? So that brings us to the end of this 2023 paper, which was the one done in October. So good luck with your exam tomorrow. If you found it useful, please share the video with your friends so we get more people looking at it, and give us a thumbs up. We do need to have more and more people. So the other day, I think we had over 1,600 students looking at our preparation. I think it was the October 23 paper for the Unit 2. So thank you to everyone coming back to look at our videos, and make sure you've subscribed, please. So once we get enough subscribers, it will definitely encourage us to take the video making more seriously. Okay, so once again, thank you, and good luck in your exam tomorrow, and hopefully see you in the next video. So if you're doing year 13, I'll be concentrating on mainly Unit 5, but it may be able to fit in another Unit 4, because my students are focused on Unit 5 and Unit 6 mainly. So we'll be putting up more videos soon. Thank you very much for watching. Bye for now.